Okay? If we have a function where we have a times x to a power, you can now skip the limit definition of the derivative. Everybody, we can skip it. And we know that when we take the derivative, we can multiply the power to the coefficient and decrease the power by 1. So essentially, if you write this down right here, that is the power rule. Nicole, did you have a question?
I just can't.
Oh, okay. Okay. If your function does not look like a times x to the n, then you cannot use the power rule until it does, if it can. Okay? A times x to a power is how your function has to look in order to apply the power rule. So some of what we do today is going to be practicing how to rewrite our function if we need to in order to be able to use it, as well as practice using the power rule. Okay. Also, in last night's homework, I made you draw some derivative graphs. Now that we know this rule, right? If you have a parabola for your function, what kind of derivative will you have? A line. If you have a cubic for your function, what kind of derivative graph will you see?
Could you show us so I didn't have to cry about my homework?
Okay, so if you skipped those problems because you didn't realize they were bolded, because I think the bolded didn't quite get printed, it was just the underline. Now you have a much more efficient way of doing it because you know the power rule. Okay? All right, so let's go through some examples. Okay. This was somebody's, was this pod 6? Was this yours? Okay, so pod 6 went through all this work of the limit definition derivative. But instead, what can we do? And I'm going to be really annoying about this just to really drive it home. Okay? We take a, we multiply it by the power, and we decrease the power by 1. 6x squared. Do you have to show me that work? No. But that's the work that you're thinking about in your head. Okay. All right, write this one down. Does this look like a times x to the n?
Yes.
Right now, does it look like a times x to the n power?
No.
This is a root. I cannot apply the power rule right this second. However, can we rewrite it? We can rewrite this as 1/3 x to the 1/3. A root can be rewritten as a power. Do it. Okay. So now, our derivative would be 1/9 x to the negative 2/3. We have to decrease the power by 1. 1/3 minus 1 would be negative 2/3. And you know what, people? This is just fine. Don't rewrite it. Just leave it as 1/9 x to the negative 2/3 power. That's all I need. Okay? Let's not create extra work for ourselves. I don't care about negative exponents. I don't care about radicals in the denominator. They're all fine. Okay? At your pod, work together on this derivative. Okay. I have stumped some of you, and I'm glad that we're having to think about this a little bit. Our coefficient is 6. What power is x raised to? Okay. I heard a lot of discussion about like the powers and the roots and all of that stuff. So first of all, we can rewrite that to a 3/5 power. But since it's in the denominator, we have to move it. Okay? That we cannot have a fraction with our x in the denominator. The x has to be in the numerator. Okay? Now we have a x to the n. We have it. All right? So now we can take our derivative. So I'm going to write y prime. Are you okay with y prime? Okay. 6 times our power would be negative 18/5. If we decrease our power by 1, our power would be negative 8/5. Yeah. Okay, let's see. We still. Okay, the tangent line problems we've kind of struggled with so far, so I want to just throw in an extra example here today. Okay, before we talk about other things that we need to talk about. Okay, we need 2 things to write the equation of a line. Shout them out. What's one?
Slope.
We need slope. What else do we need? You don't have to have the y-intercept. That helps. We at least need a point. Okay, y-intercept would be fabulous. But if we have a point, if we have slope, boom, we can write the equation of a line. Okay? Now I'm writing the equation of a tangent line, which means we need to find the derivative so we can find the slope. Okay? Ray Sparson. What's our derivative?
I was still working on the last problem with Turner.
Uh-oh.
Wait, I'll do it. 15x squared.
Okay. Did you have a question up here or were you just
I think I got it.
turn your friend?
Yep.
Okay. Are we okay with that derivative being 15x squared? Okay. Is our slope 15x squared? It is at any given point, but if I'm talking about x equals 1, is our slope 15x squared? Okay? We would need it to be 15 times 1x squared. Right? Okay. What else do we need before we write the lines? Do I have enough? I have enough. Well, this is our slope. I have an x value. Okay, we do need our y value of 5. Okay? Now we can write y minus 5 equals slope times x minus x. There's our tangent line.
You're just asking me
Figured it out? Okay. Questions about the tangent line. Slope and a point. Put them together. We have our tangent line.
So we got that slope because we found the derivative.
Yeah.
And it's at x equals 1. So
Yeah. Okay, I'm going to repeat what Colby said. We got that slope because we found the derivative and we plugged in our coordinate. Okay. All right. Now, how many equations do you see that are just 3x squared or 5x cubed or just like one term, right? Not many functions are just one term polynomials, okay? So I want you to understand, and you don't even have to write this down. Here, don't write this down. Don't write this down, okay? And you don't even have to write this down. But if you have functions that are being added or subtracted, we can take their derivatives individually, okay? I think that that's something that some of you probably were just going to assume anyway, but I want to make it official, okay? If you are adding or subtracting like terms like 5x squared plus 3x, we can take their derivatives individually and add them together. That's what that's saying. Also, if you have a constant outside of your function, you can either take the derivative with it, or you can take the derivative and then multiply by the constant. The constant just goes along for the ride. Okay? The constant is always being multiplied. Okay? Yep, so that you remember. I know it's misspelled. Okay? I know it's misspelled. Okay? Lets me know who's paying attention. You passed the test. Okay. This is going to become more important with other rules that we learn. Yes, we will learn other rules so we don't have to do the limit definition every time. Okay. 2 of those rules are this right here. Write them down, circle them, star them, highlight them, make them obvious to you because you need to remember them. The derivative of sine equals cosine. And the derivative of cosine equals negative sine. The derivative of sine is cosine. And the derivative of cosine is negative sine. There's nothing I can do for you but tell you you have to remember those. Okay, so essentially you know that sine and cosine are connected, right? You just got to remember, is it going to be positive, is it going to be negative? Okay, the derivative of cosine is negative sine. Did you forget that, Eli? Okay. Now, typically I would take a moment and show you why the derivative of sine is cosine, but I'm going to go ahead and skip that so we can do more examples. Is that okay? Do you guys just believe me that this is true?
Yeah.
You're okay with me not showing you? You will probably have a question like this on your quiz on Wednesday. I'm going to be very straightforward with you. Not really. You'll get a review. I think. No, don't call me on that. I don't remember. No, there's not going to be a review. Just We're just gonna have a quiz. It's gonna be fun, Nicole. It's gonna be fun. Over here. Okay. Okay, I said quiz and everyone's eyes got big. First of all, it's on your goal sheet, right? On your goal sheet. Okay. On your quiz, and we'll talk more about it tomorrow. You know you're gonna have a limit definition problem. You know I'm gonna ask you the definition of the derivative. You know I'm gonna ask you power rule questions. And I'll tell you straight up there's gonna be a tangent line question on there. Okay? We've done problems like everything that's gonna be on the quiz. Just take a deep breath. Okay? What is wrong with this function? It is ugly. Can we apply the power rule right now? We cannot. However, in our denominator, we have 2x to the 1/2 power. So if we can take this and make individual terms, we can use the power rule 4 different times. So, watch this. So let's just think of this as 2 times x to the 1/2 power, okay? So when I take 2x cubed and divide it by 2x to the 1/2, we really have 1x to the 5/2, because we subtract our exponents when we divide. Yeah. Okay. Negative 3x squared divided by 2x to the 1/2. Our term would be negative 3/2 x to the 3/2 because we subtract our exponents. Seven x divided by 2x to the 1/2 would be 7/2 x to the 1/2. And then plus 5 divided by 2x to the 1/2 would be plus 5/2 x to the negative 1/2. Rewrite each individual term, and so now we have 4 power rule setups. You see that? Ax to the n, Ax to the n, Ax to the n. Before we take the derivative, any questions on how I got those 4 individual pieces?
Could you not do it like while it's still in that form? Could you not?
Since that is not Ax to the n alone, we can't take the power rule.
What if it was? Could you? Like if it was just 2x on the whole or something?
It still would not work. It still would not work. We have to have individual terms in order to be able to apply it. Okay? Which is why we're going through this example so you can see why we have to rewrite it. Nicole and Anthony, do you have something that?
Is that one over?
Nicole, can I answer your question for you? Uh-huh. Okay, well, it's still in the denominator. So if I move that up to the numerator, it would be negative 1/2. But right now it's still in the denominator. And what I did is I took 2x cubed divided by 2x to the 1/2. And I subtracted the exponents. So it's like we have that negative exponent. I just kept it downstairs. Does that make sense? Okay. So now let's talk about your derivative. Okay? 1x to the 5/2. Bring down the exponent and then subtract 1 from your exponent. 5/2 x to the 3/2. Okay? Our next term, power rule again. We have negative 3/2 x to the 3/2. We take our power and we multiply it out in front. Decrease our power by 1. And again, 7/2 x to the 1/2. We take our power and we multiply it out in front. Decrease our power by 1. And then our fourth term. 5/2 x to the negative 1/2. We multiply our power out in front. Decrease our power by 1. Leave your answer like that. There's no need for us to even try to simplify that. I'm fine with negative exponents. They're perfectly fine. Two more examples, right? This is example second to last.
So we're gonna do
Our derivative. We have two terms. Colby, I overheard you. Are we need to like separate this out? We have two terms, so we're going to think about two derivatives individually. Okay, first we have x. The derivative of x would be what? 1. Plus the derivative of cosine is negative sine. So I'm going to go ahead and change this to negative sine of x. We're done. Yes.
Just for the last one, you put d of y over dx.
Mhm.
Can I just put y prime?
Yes, they are interchangeable. Okay. Y prime is a lot less to write. Okay. Do y dx, y prime, whatever you write is fantastic. All right, last example. Okay, does this look like a times x to the power? It does not. It does not look like ax to the power. So what we're going to have to do is you're going to have to multiply that all out to where we have individual terms. And then we can apply the power rule. Okay? So this is 9x squared plus 12x plus 4 if we multiply that out. Do you agree with that? Then we can multiply to 9x cubed plus 12x squared plus 4x. Now we have individual terms that look like ax to the power. Now we can apply the power rule. Okay, some of you are annoyed that we're having to multiply this out. Later on, I will teach you a way to where we don't have to do this to take the derivative, but right now this is the only way. The only way. So now 9x cubed. 27x squared. 12x squared. 24x. And 4x. 4. Okay? I tell you what. The book will probably write their answers a little bit differently than me. So what I'm going to do is during my plan period, I'm going to write out how I would expect your answers to look. And I'll upload that PDF at the end of the day. So you can check your answers with mine to see exactly how I want them to look. Does that make sense? Okay. Let me stop the recording.